Okay, so we're going to talk about Unit 4, Worksheet 2, Interactions. Now, when we're looking at these interactions, we need to use our first and third law of motion that we've talked about in class. The first law of motion states an object at rest stays at rest, and an object in motion stays in motion with the same speed and in the same direction, unless acted upon by an unbalanced force. Now, that explanatory statement we have that goes along with that states if the sum of the forces are equal to 0 newtons. That means the motion is not changing. Another way of thinking about that, and we can end up writing it as if the velocity is constant, the forces are balanced. What that means is if our velocity is 0 meters per second, that means it's not moving, it's at rest. As long as it continues to have a velocity of 0 meters per second, remaining at rest, the forces will be balanced. But also, if an object is moving in a certain direction with a certain speed, as long as it continues to go in that same direction with that same speed, with no change in its motion, those forces will remain balanced. That is going to be very useful for this first law of motion to allow us to determine the amount of force acting on a single object to see if the forces balance out or they do not for all the forces acting on a single object. The third law of motion states, for every action, there is an equal and opposite reaction. This law does not apply to the forces acting on just a single object. Instead, what it allows us to do is to relate the amount of force acting on one object to the amount of force acting on another. These can only be related if those two objects are exerting a force on each other. What we have here on this page is showing that if we're looking at some type of force on object A by object B, we can have the same type of force on object B by object A. All that's really changing here is the victim and the agent. It's the same type of force though. We're just changing who's exerting the force. And then also the only other change that we have is the direction, which we represent with the sign. It's the same value, the same number, the same amount of force. But the direction is different when we're looking at these two separate force diagrams. We can get practice looking at that with problem 4 on Unit 4, Worksheet 2, Interactions. We have two objects here, Block A and Block B. The question wants us to find out, how does the force Block A exert on Block B compared to the force Block B exerts on Block A? In order to answer this, we're going to draw and label a quantitative force diagram for each block using equality marks on the vectors. So we're going to have these two objects here. We're going to have object A. So we're going to draw a force diagram for all the forces that cross this system boundary right here. Acting on object A, which has a mass of 100 grams, or we can relate that to the mass we use in physics as 0.100 kilograms. So that's going to be our first force diagram, is the forces acting on object A. The second force diagram is the forces acting on object B, so we're going to see what forces cross this system boundary. Once again, we can take that 50 grams and convert it to what we'll be using in physics as 0.050 kilograms. One thing that we need to remember about this is the velocity here is 0 meters per second. We have no indication that it's speeding up or slowing down, so we can say that the sum of the forces acting on block A and on block B is 0. This is true horizontally, and this is true vertically. So that's what we're going to be focusing on when we're going to be looking at these force diagrams. We're going to have two of them, one for object A and one for object B. Now, it does say to draw quantitative force diagrams, and we will. However, the first step to drawing a quantitative force diagram is to draw a qualitative force diagram. So we're going to start drawing a qualitative force diagram for all of the forces acting on object A. The first force I know is going to be acting on this object is the force of gravity, because this object has mass. So I'm going to be drawing a downward force of gravity on object A by the Earth. Then after that, I'm going to look for any other non-contact forces, such as the magnetic or electric forces. I have no indication that those are here, so we don't need to worry about those non-contact forces. So that just leaves what is physically touching this object. What is crossing that system boundary? The only thing that is touching it is going to be object B that is directly beneath it. It is going to be exerting an upward force, that push up on object A by object B. And because it's a push up from a surface in contact that is 90 degrees to the surface in contact, we know that's going to be a normal force. Because that's the only other thing acting on it, and I know that this thing should have a sum of the forces equal to 0, I'm going to draw this normal force on A by B equal in size to the force of gravity on A by the Earth. I know that because the arrows are drawn the same length, but I can also add congruency marks to make that explicitly clear, as well as account for that in my sum of the forces equation. Now I could do one for both x and y, but right here, the only ones that are relevant are the sum of the forces vertically, in the y direction. I know it should be equal to 0 newtons, so I'm just going to account for those two forces, that force normal, up, and that force gravity, down. This is a way that we can account for this. This right here is a qualitative force diagram, what we have lots of practice with. However, we do need to make this quantitative. This is where we can ultimately use the equation we know from our spring scale lab. To quantify a force, we can only quantify the force of gravity so far. So to quantify this force of gravity, it's 9.8 newtons of force for each kilogram of mass. We have for object A 0.100 kilograms of mass. 9.8 times 0.1 is 0.98. The kilograms cancel out, leaving us just with the units of force, which is newtons. So I have my force of gravity as 0.98 newtons. And because I know that that upward force needs to balance it out, that upward normal force on A by B should also be equal to 0.98 newtons of force. I was able to relate the quantities of those two forces by taking what I know about the first law of motion. The forces need to be balanced, the same size, because there is no change in the motion. For when we have all of the upward forces balancing out with all of the downward forces. That's going to be it for our force diagram for object A. Object B, we're going to have a different force diagram. We're going to have, well, starting off with a force of gravity, pointing downwards on B by the Earth. However, I know the mass of object B is half that of object A. So I'm going to qualitatively represent that by drawing a downward arrow, half the length of the force of gravity on A by the Earth, to indicate that it should be less force. So I have that downward force of gravity on B by the Earth. No electric or magnetic forces here, so I'm going to see what's touching it. We have the ground underneath it, pushing upwards with that normal force, but we also have A pushing down on B straight downwards. We need to account for how much force that is going to be in each direction. We know that A and B, because they're touching each other, exert the same amount of force on each other in opposite directions. That's what we can mean by our force pairs, or the third law pairs. We've already identified one of them. We have the force normal on A by B. That's going to be paired with something that's in the opposite direction. It's still a force, it's still a normal force, but we swap those last two terms. Now this normal force is on B by A. So this force right here, that's pointing upwards, is paired with a downwards force acting on object B, which is what I'm going to represent here. We have a force normal on B by A. That is the same size as those forces on the left force diagram. We also still have to account for that force the floor is exerting on object B. It's pointing up. We know that the sum of the forces acting on B needs to be balanced. So we need to have a single upward force that is equal in magnitude to the combined amount of force downwards. That's why it's going to be a big arrow. It's that push-up from a surface in contact, so it's a normal force. It's on B, but it's by the floor. This right now has accounted for all of the forces we have acting on B. So we need to write the sum of the forces equation. I'm just going to keep it for the relevant vertical forces here. It should be balanced, 0 newtons. We have that one upward force, that normal, on B by the floor. And we have two downward forces, that normal on B by A and the force of gravity on B by the Earth. This right now is a qualitative representation of the forces acting on B. To make it quantitative, we need to do what we did for object A. We can start off by quantifying that force of gravity, 9.8 newtons of force for each kilogram of mass, but now we have 0.05 kilograms of mass. Our kilograms still cancel out, but now we only have 0.49 newtons. Previously, we knew that the amount of downward force was equal to the amount of upward force because we only had those two forces. But now we also have a second downward force. So we need to quantify these other two forces in a slightly different way. We are able to quantify that downward force normal on B by A because we do know it gets paired with that upward force normal on A by B. If it's 0.98 newtons up for the normal force on A by B, it's 0.98 newtons down on B by A. So we know the quantity of these two downward forces, but we need to be able to quantify that upward force. That's where I'm going to rearrange our sum of the forces equation. I'm going to say that the force normal on B by the floor is equal to the combined amounts of the force normal on B by A and the force of gravity. I can plug in the values I know for both of those two terms. I know force normal on B by A is 0.98 newtons of force, and I know that force gravity is 0.49 newtons. So the force normal on B by F is 0.98 newtons plus 0.49 newtons, which is 1.47 newtons of force. 1.47 newtons is the last quantity I need to add to that force diagram. That one is now fully quantitative. This one, I had to apply what I knew about both the first and third laws of motion in order to quantify it. Now back to the original question though of problem 4. How does the force block A exerts on block B compared to the force block B exerts on block A? Well, we had to use that relationship in order to quantify both force diagrams. The force block A exerts on block B is equal and opposite to the amount of force that B exerts on block A. So it's an equal amount of force in the opposite direction.